right.
Now we're going to look at called capital F, and I said, okay, we can compute f of n using dynamic programming in O of n time by computing starting from f of 1 all the way up to n. However, it's possible to do it faster. In particular, it's possible to do it in logarithmic time using memoization. So here's the recursive definition. So what we will assume is that we have a sparse matrix with the operators store and fetch. We also have a Boolean question as to whether the value of f of n has actually been computed and stored. So the default position is to return that the answer to this is false. And then after a value has been stored with store, then this comes back as true, and when we fetch, we get the stored value. All right, so the execution of this is relatively simple. We first, of course, have to initialize the sparse array, which we'll call capital F. And then what we have to do is execute the code. So we're given f, so we have the function f int n. Now, this could have any type. We could say that this type is int. We might as well do that. And then when we put in a parameter n, and then the first thing we do is we ask whether it exists. Whether the function capital F of n has already been computed. Well, the answer could be true or false. So, if that's true, then we return the value of fetch f of n. So we fetch that value out of the sparse array and return that value. All right, now, otherwise we're going to go through a process here. We're going to say, first of all, the value has not been stored. So we say if n is less than or equal to 2, then we store the value f of n equals 2. All right, now otherwise, we're going to compute one of these two things. So we're going to say else if n is even, or n is odd, I guess that would be what that means. Then we're going to compute the value, the odd value, by fetching it. So, of course, I don't have to write fetch. We're assuming that it automatically fetches when we request that. So therefore, otherwise I'd be too busy here. So what we'll do is we're going to store the value of fn equals, and then we will fetch this value here, f of n plus 1 over 2. Now, n minus 1 over 2 squared plus f of n plus 1 over 2 squared mod 23. So we'll compute this value here using fetch, and then we'll store that value. And then, else, we'll do the same thing for the other formula. N over 2 times f of n minus 2 over 2 plus f of n plus 2 over 2. And each of these will require fetching. And that's, of course, mod 23. Now, this would be, of course, the end of that branch. So this would be a beginning branch here. And actually, I don't think I need squiggles there. But I need to have a squiggle here and squiggle there. So this would be the actual code. Now that's only pseudocode. Of course, it totally neglects all the operators you'd have to write. You'd have to write all that. And the question is it worth it rather than using an array? And the answer depends on how big n is. If n is something really seriously big, like 1 trillion, then it's worth it, because you don't have 1 trillion spaces in memory. But if you only have to store the log of 1 trillion, which is on the order of 40, that's the base 2 logarithm of trillion is approximately 40. So that's very little storage at all, and so you can do it. All right, here we're trying to find the strong components of this particular directed graph. Now, at first, what we do is do a depth-first visitation of all the nodes, where we're going to visit them in alphabetical order. Now, that order is truly arbitrary. If we change the alphabet around, we would get different numbers, but we would get the same final answer. So we'll go alphabetically, and whenever we visit a node, we'll write the next number in our sequence. All right, so now I see we're going to a 2 here with depth first search. And we follow depth first search, we get a 3. And then here, I suppose we get a 4, right? Now with depth first search, we get a 5 here. And then this will give us a 6. And after that, this one has no remaining out neighbors that haven't already been visited. So we have to back off. At this point, we have a stack with these items this way, but now the F will be popped from the stack, and so we give it the number 7, and the G will be popped from the stack. We give it the number 8. All right, now we're now at 4 is at the top of the stack, and what we do next is we have an unexplored vertex here, so we'll give that the number 9 because that's the next number in our sequence. Then we can see this, that's a 10. All right, now we have no further neighbors there, so we pop that one off, and then the next one we pop this off, and the next thing we do is pop this off. Now we pop that off, and now what? We are back here. We can't pop this off because it has a neighbor that has not yet been explored. So that neighbor is 15, and this one is 16. Now finally we pop this off with a 17, and this is an 18, and finally we pop 19 off. All right, now that's our first depth first search. There will be a second depth first search. Now, I want to point out to you that there are several known algorithms for finding strong components. What I am showing you is how to work this problem with the one algorithm that's given in our textbook. All right, now at this point, what we will do is we'll do depth first search on the reverse graph, where it's understood then that we begin. Now we don't get choices here. We have to begin with the numbers which are largest. So we give these priority. We're going to look at this one first, and then this one, and so forth. But once again, we use the rules of how to, we always look at anything that can be explored from there. And if the stack becomes empty, then everything that was on the stack in that round becomes a strong component. So we start by pushing B because that has the largest number. So we give this a 1, then we give A a 2, and C a 3. Now, what happens here? We start popping, and all of a sudden the stack is now empty. And because the stack is now empty, all the items that were on the stack since it last became empty become a strong component. So this is a strong component. Now the stack is empty. We go to, and we look at these values here. What's the largest remaining second value up here? Well, it's 14. So these are already taken care of. So therefore, this will be our next explored vertex with a 5. On the other hand, now we can't go anywhere because the arrow goes the wrong direction. So we also get a 6 here, and the D is popped off the stack. And the D was the only node that was on the stack during that round. Now the stack is empty again. All right, we go to the next largest thing that's not taken care of. That's the 13 for its E. All right, so what do? We give this a 7, and we can see this is an 8. This is a 9. Now there are no further things there. 11, it's 12, 10, 11, 12. And now the stack is empty again, which means we found another strong component here. All right, now we still have some nodes left over. So what's the largest second number up here? It's a 12. So that means that this node is a 13 here, and then that can be reached a 14. Well, there's nothing left, so that's a 15. That's a 16, and now the stack is empty again, and therefore this is a strong component. Now, we have covered all the nodes. If there were any more, we would do them now, but there aren't, so we're done. And these 4 sets are the strong components. All right, now the next thing we're going to do is the next problem, which is problem 11. 12. That was problem 11. All right, now, we're given an arbitrary sequence of numbers. We might as well assume they're integers. And we're going to stick in a fictitious number, negative infinity. And here, we're writing the indices of the numbers, so the fictitious minus infinity will have a 0 in it. Now we're going to have an array of back pointers. We're also going to have another array, which for each node here, for each number, represents the longest monotone subsequence that ends there. Well, when I look at this, the correct back pointer is this way, and the monotone subsequence that ends there that's longest is just 5. All right, now, at this point, we need another array here. What we need is an array which basically tells you what the best choice of node which has a certain 1 there, that has the value 1. So we have 1 here, 2, and the best choice is 5. Perhaps I should put a different color there. I'll make this 5. All right, now we look at these entries one at a time. We see a 1 here. Now what we do is we look for a number that is smaller, the next number that is smaller than 1, which is minus infinity. Now this means that we have a better choice than the 5. So 1, that means that the shortest that the longest Munson sequence that ends at the second position has length 1. Now what that means here is that, well, this was not a 5, we're supposed to put the index here. So we put the index 2 at this point, indicating that this index 2 is the source of is the last term, the last index of the best subsequence of length 1. Now we still don't have one of length 2, but we're going to get one now. We try to find something that it can attach to, and that's the 1. And so that means that this is 2 here for 3. So this 3 refers to that here. This is also in the same column. And I'll just move these over a little bit so it's clear. This 1 is under this, this 3 is under that. And this 3 means that, no, this is 2. This means that we have length 2 here for the best choice of a Montan sequence that ends here in position 3. All right, so what we'll do is, for length 2, we'll write 3 here, which is the index of that position. Now we move over to the 4th one. Now, I notice the 7 is allowed to attach to the 2. Very good. We like that. And so we put the word 3 here. And we have finally 3 here, and the result here is that it's in position 4. So that means that in index, we're not going to get a subsequence ending in 0 that has any of these numbers in it. So its back pointer is negative infinity. And what we put here is a 1. Now, we already have this 2 here, which means that the best sequence of length 1 ended here in position 2. But now the best sequence ends in position 5. So this is crossed out and replaced by 5, because this sequence is better than the previous one. All right, now let's look at index 6, which has a 9 in it. Well, we're looking for something that is smaller than 9 and has the maximum value in this array, the length array. And that would be position 4. So that means that we will be able to build a sequence of length 4 ending in position 6. All right, now that means I have to expand this array, and I put the value 6 here. All right, now we're done with that. Now let's go to position 7. I can't attach a 3 to the 9. I could attach it to here, but I want the largest value here. Can I attach it to anything that's larger than that? Well, this 3 can be attached to 0, but that doesn't help much. Can it be attached to the 2? Well, yes, it can. And that's the best choice. But that means that the best subsequence that ends in position 7 has length only 3. But that's okay. It's a better choice than the previous one we had. So this one becomes irrelevant now. And we now have this in position 7. All right, so what is our current situation? The best sequence that ends with just length 1 ends here. The best sequence that has length 2 ends here. The best sequence that has length 3 ends here. And the best sequence that has length 4 ends here. Now, it seems to move around, bop around a bit, but that's the way it is. Now let's look at this 8th one here. This can attach to that, which means we now get a sequence that has length 5, a subsequence of length 5. And so we can put a 5 there, and that doesn't eliminate any of these numbers. They're still okay. All right, so now we have a subsequence of length 5 that ends at in the 8th position. And now let's look at this. This is an 8, position 9, and you look at that, and what can it attach to? It can attach there. And 1, 2, 3, but wait, hold on. This is a 4, isn't it? I'm mistaken, this is a 4. And so, this one, I'm sorry, this one deletes this. This isn't 5. This deletes this. This was 6. And now I'm crossing it out and making it 8. All right? Now, this passes to here, which means we now get a subsequence of length 5, which ends in position 9. That doesn't cause any of these to be crossed out. And we're now done. The back pointers are shown here, and we can now reconstruct the best sequence. It's 1, 2, 3, 5, 8. So we start at the largest value here, the largest best maximum length here, the starting in position 9. And we follow the back pointers back to get the sequence, not counting the 0th position and the fictitious minus infinity.